Hello everyone, my name is Valeria de Paiva. I work in Topos, and when I first was invited to talk in the Finding the Right Abstractions workshop, I was delighted. I thought it was brilliant that I could possibly put together some of the work that I did many years ago, kind of straight out of my PhD, with some of the work that I've been doing in the last 20 years working for companies in Silicon Valley, such as Samsung and Nuance, that create AIs for commercial uses. So I thought it was an ideal, an awesome sort of opportunity for me. But I wasn't expecting some of the discussions that we've been having between the two different communities and how it's not so easy for them to talk to each other. I think I wanted to kind of see how we can go about discussing some of these issues. So this is work with Samuel Gomes da Silva, who is a Brazilian logician, and I want to talk to you about Dialectica and Kolmogorov Problems, which are related to Scott Garaband's Cartesian frames, or two spaces. So I have to admit that, it is true that this is a famous quote attributed to Goethe, and that mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it's something entirely different. I think it's kind of true, and we normally do translate things into our own problems and the stuff that we actually want to solve. And I'm not going to be very different from anyone else in this meeting so far. I think everyone has done a little bit of deciding that the right abstractions are the ones that they want to solve, and that they should be solved the way they want to solve them. But the title of the workshop does let you do that, right? Because finding the right abstractions depends very much on abstractions of what, on where you want these abstractions to be, and most importantly, abstractions right for what goal, what finality. And if you just kind of try a totally silly thing like asking Google finding the right abstractions, it gives you Stack Overflow generic advice about finding the right abstractions of programs, but this is too low a level for us. And if you think about it as finding the right abstractions for mathematics, well, clearly you then need category theory and the Curry-Howard correspondence, but you might end up in a talk for philosophers of mathematics, and that's not what we are here, I think. So what I decided to talk to you about finding the right abstractions is, I think we want to talk about finding the right abstractions for reasoning in general, because reasoning is what connects AI and category theory and categorical logic, which is the third side of my approach to this problem. So I want to talk to you about category theory and Curry-Howard correspondence for problems and solutions. And one thing that I did not know much about until very recently is that Andrei Kolmogorov, in his 1932 paper on the interpretation of intuitionistic logic, which was published in 1991 in English by in his selected works, kind of had a very important idea on how to think about problems. This insight of Kolmogorov's is actually similar in lots of ways to the insights that Andreas Blass had in 1995. And Andreas kind of wrote in a paper called Questions and Answers, a category arising in linear logic, complexity theory, and set theory, in 1995, that a category used by de Paiva to model linear logic also occurs in Vocha's analysis of cardinal characteristics of the continuum. Its morphisms have been used in describing reductions between search problems in complexity theory. Now, I find this quote extremely interesting because, to begin with, there is no reason why models of linear logic should be at all related to set theory in the shape of cardinal characteristics of the continuum, and it certainly has no a priori reason why the morphisms of this category should be used in complexity theory. But the fact is that they are, and that the category is used in these places that Blas is mentioned, and also in many other places. In particular, the category has recently reappeared under the influence of Scott Garaband as another version of the Cartesian frames, a dialectical version of the Cartesian frames, as a way of thinking of multi-agent interaction. So Andreas calls this category PV for Paiva and Voces, and the objects are binary relations between sets. So they are triples, A minus, A plus, and A, where A minus and A plus are just sets, and A is a binary relation between these two sets, so A is contained in A minus times A plus. You might prefer to think about that using Scott's example of the Cartesian frames, and then you have, as Scott kind of nicely put, you can think about the fact that there might be rain, or the sky might be sunny, and you might have an umbrella, or you might not have an umbrella, the N for no umbrella. And you could even think about that as a nice picture like that, all the possibilities being calculated. And I just had to make I thought it was better to make a different shape a different emoji for the non-rain, and there's a quote there. But it gets too hard to do these things too soon, so I think we're going to carry on thinking about sets as A minus and A plus, and the relation A between them. Now, the important thing about this category is, as usual in category theory, how objects relate to each other. So a morphism from A to B, or B is again a B minus, B plus, and a B, is a pair of functions, F minus from B minus to A minus, and an F plus from A plus to B plus, such that for all B's in B minus and for all A's in A plus, we have a relationship that Stuart Armstrong was very nice to kind of describe for us yesterday, except that he had a version of that where you had equality between A of F minus of B, A, and B of B little b and F plus A. So he had an equality where I have this implication, which I kind of try to read as some sort of lax structure in the category theory, but you can just read it as less than equal. So we're just thinking that there is an order. There is an order between true and false, and the relations have to satisfy implication in this order. So the main thing that we have to consider is that we have this morphism from A to B, the way we described a minute ago, and I want you to think about an object of this category as representing a problem, and the elements of the A minus are the instances of the problem, and so specific questions of this type, and the elements of A plus are possible answers, and the relationship A between the A minus and the A pluses represents correctness. So A of xy means that y is a correct answer to the question x. Now, that kind of vaguely presupposes that you know which ones are the questions and which ones are the answers. And for dialectica, we don't really know very much whether something is a question and answer, so we can't actually call them use and axis and call the relation alpha, because we kind of thinking that use are unknowns and axes are variables, and they can be related both ways. So I could give you a few examples of objects there. So you could think about, say, the natural numbers, and the natural numbers with equality. So n is related to m if and only if n equals m. We could think about a much more complicated relationship, like you have as objects all the functions from n to n, and the second object is being just n, and you say that alpha is defined by a function f is alpha related to n if and only if f of the particular n that I picked up is the same thing as n. And you can do it for finite thing. You can do the same for the real numbers, and you can do the same for objects, more limited objects, like the objects in true, that is just the true and false. So you can think about the equality between true and false, or the inequality between true and false. And we have a collection of results dealing with that. So what I'm proposing to talk to you about today is this notion of a theory of problems. And for a theory of problems, we normally have to discover what's the unknown, what are the data, and what is the condition that the data has to satisfy. So this paper that this work is based on appeared very recently in a volume for Professor Paulo Veloso, who you've seen there. And Paulo Veloso mentioned that Kolmogorov was the inspiration for his theory of problems, and that's the reference for his paper. But we didn't want to kind of the formalization that Professor Veloso did. It's going to be slightly different, and will take us to the main points of the paper that this talk is based on. But that's not what I want to talk to you about today. I want to talk about the original work of Kolmogorov, where he kind of had a very similar idea. He has that a problem is a triple P, which is a set of instances of the problem, a set of solutions to the problem, and where sigma, a solution-like thing, is as a set theoretical relation. And what he did with these problems of his, and that's this very interesting thing, is that he provided an alternative intuitive semantics for propositional intuitionistic logic. And that means that, that is the reason why K is part of the BHK interpretation. BHK stands for Brouwer, Heiting, Kolmogorov. And the way that Kolmogorov starts his paper in 1932 is by saying, if you don't believe in intuitionistic logic, no problem, this paper is for you. If you do believe in intuitionistic logic, you can read the second part as well. But the first part is for every mathematician, not just for logicians or people who have problems with foundations of mathematics. And he says, we never assume that a problem can be solved or is solvable. Now, what we kind of do in the paper that I say is the basis of this work is to show that the Kolmogorov problems are dialectical sets, actually objects in the category diode-2 sets op, which was the main thing in my thesis in 1988. And we do have similar morphisms. And the difference between these dialectical sets or dialectical spaces and the Garaban's Cartesian frames or the two spaces is that it's exactly the difference in the definition of the morphisms, is the existence of this implication that we discussed a minute ago, as opposed to one equality. So the existence of a morphism from P to P prime, from a problem P prime to problem P, ensures that there is a reduction of the problem P to the problem P prime. And I think the fact that we want to reduce problems of a bigger complexity to problems of a smaller complexity is important. So I have only two examples to show you, and I have 5 minutes according to my watch. So I wanted to show you one example that is a total simple example that we kind of have to, that we learn in kind of elementary school about. It's just a very beautiful example, it is the fact, it is why Descartes kind of managed to transform geometry into algebraic equations, but it's just simple by now, right? So the example is as follows: you think about a coordinate system for a plane pi, any plane pi, and you think about the coordinate system for this plane by saying that you have a function that takes a pair in R2 and goes to pi. So P, capital P is the same thing as f of uv, and the coordinates in R2, u and v, give you the location of the plane pi, of a point in the plane pi. A line of P is then an equation of the form ax plus by equals c, and that's the beauty of Descartes' work, where a and b are real numbers and they are not both equals 0, and c is either 0 or 1. And we can name the family of all equations of this form E, and you can denote by L, calligraphic L, the family of all lines in the plane pi. And you can also think of the function EQ of L, which is the canonical equation that represents a line L. Now here, the two Kolmogorov problems that we have are, the first one is to decide whether a given point, UV, lies on a given line L or not. And then you can represent this problem simply as cal L, calligraphic L, pi, and the opposite of belonging, because you're saying that the point P in pi lives, sorry, let's try again. We have a point UV, and we want to know if it is in the given line L or not. So if the point is in the line L, then we satisfy the problem L pi, the opposite of belonging. And the second problem that we have is to decide whether a given pair of real numbers satisfies a given equation. And that you can think of it as being the problem E R2 chi, where an equation is chi related to a pair of points if the points, when substituted in the equation, give you an equality. So this is very trivial. It's not. I'm not doing anything difficult here, but But you have to do some work to show that the problem 1 is reducible to problem 2, and you have to do quite a bit more of work, but more interesting work, to show a second problem, the problem of tangent planes. So if M is a two-dimensional differential manifold, we think about, we have the manifold M, which is contained in R3. You have a point X in the manifold where there is a tangent plane centered at X. The line L through X is the normal line of the plane, which is not drawn there. if it's perpendicular to all the lines of pi which go through x. So you have to think of something going up from here. You have, as before, L, curly L, the family of all lines, and curly P, the family of all planes. And the problems here are to find the normal lines through each point of the surface and find orthogonal planes where two planes are orthogonal if all the lines, if all the lines of one are orthogonal to all the lines of the other. So we can reduce problem 1 to problem 2, and what is interesting about the second problem is that, so here we have this thing about little f and capital F, and the little f simply says that if you're given a point x in the manifold, you can give me back the tangent plane for all for that x, the whole tangent plane on that x. Much more complicated is the capital F morphism, which takes an x and a plane rho, and gives me back the phi of the tangent plane rho and x, where the phi is the line contained in the plane which is perpendicular to the intersection line of pi and t of x rho, if pi and rho are orthogonal planes. So what we're trying to do is that thinking that we are trying to do a minute ago here, where we are saying that to define orthogonal planes, we need to think about all the lines going through x, and how they are all orthogonal to the normal line of the plane. And you know, the thing that kind of happens in this reducing of problem 1 to problem 2 here is that we say that we reduce the problem of finding all the tangent planes to a certain manifold to the easier problem of finding whether two planes are perpendicular. And this is a huge simplification, right? Because we transformed a manifold problem into a problem of planes. But in this case, the map little f, capital F, needs to refer to the point x where we are doing the tangent plane. So a reduction in this case is not just a morphism of the first kind of Dialectica category, or the case of Dialectica category that Scott calls Cartesian frames, but in this case we actually need to use the kinds of dialectica that are really related to Gödel's dialectic interpretation. And this whole subject seems connected to automated differentiation and lenses. So I finally concluding by saying that the categorical connection between these dialectica models, Kolmogorov's problems, and Blas's problems shows us that the use of categories really allows us to connect extremely different areas of mathematics using very simple methods. The main theorems of the paper that I'm discussing are about the axiom of choice and how different versions of choice will lead to different classes of problems. But while Kolmogorov and Blas do not require the axiom of choice, Deleuze's notion will enforce it, and we will not in our categorical model. For me, the surprise of starting with models of linear logic and ending up with an abstract notion of problem that applies to number theory, analysis, geometry, functional programming, multi-agent modeling and AI, and many others, was the biggest pay back the wonderful, awesome surprise of this work. So I think I just leave this quote from Jane Gowers for you to think about. And it is about how we category theorists kind of want everyone to think about the similarities in mathematics between different kinds of problems and solutions. Thank you.